Okay, so before I get started with the talk, I just want to share a small story that may relate to the previous presentation about why we started to use Elixir. Uh, and it started in 9 years ago, in 2016, when a client sent us a click log with 20 million clicks. There was one day of data, and they came with a problem. It was on the network. They came with a problem where they said that they had some fraud in their in their transactions, and we were doing some machine learning back then, data processing, etc. They wanted us to find the fraud to establish a malware keys to help them event. And so back then we were also doing a lot of Ruby. We managed to make it work. We were doing a lot of the processing, ETL, etc. And we managed to make it work. It's a lot of multi-processing DAX. It was working, and they liked it very much. They bought it. They bought the solution. We sold it to a couple more customers, and then one day there was one that came with a 2 terabyte log file with two billion impressions, and became slightly more problematic to get the process done in time. And so back then we started to just spend all our day maintaining the loop, just trying to keep it working. We're not able to work on any new features. Everything was crashing left and right. And we needed to get out of there. Multiprocessing was okay in the beginning, but then because of memory issues, because of other types of synchronizations, were just unmaintainable. And yeah, we need to move on. So we evaluated a lot of stacks at the same time for those needs. We had a couple of needs. One of them was processing, obviously. The other one was reporting, so dashboards. A lot of what seen in the first presentation, came from bins, iterative dashboards, lots of data there as well, breakdowns. And we evaluated C++. We had a lot of experience with C++ back then. It's too painful to use. Go was a very good alternative. Then we had Scala, it was very small. I didn't do the tech with it at the time. And Elixir, honestly, it's the first time we used it. I didn't like it at all, but we gave it one more try. We had a small project with it, and we saw all the benefits that were described in the previous presentation. The thing we cared about, like I said, were the control over the hardware, so memory versus CPU usage and things like that. And having a very good web framework. The other points, reg tooling, documentation, the simplicity, the developer experience was very important. We had a very small team. We still have a very small team. And like we saw, all of it is included. Yeah. Maybe the last point, it is really worth highlighting again. We can reuse all of the Erlang ecosystem. So there's a lot of libraries that are already developed beyond what's available in Elixir, and there's 100% compatibility. And got us to today. So today we are that's by the F. We are processing millions of requests a day. We have to classify. We have about 5 product lines handling fraud across several types of industries. I mean, and different problems. But about 600 customers use it. If we include agencies and partnerships, this goes by maybe double. And although initially we're doing only fraud detection, we're now expanding into market security as well. Today, we're just going to talk about one small problem of what we do, which is how to detect fraud with a web request, within a web request. Okay, think about detection. When you have a website, you have a fraud happening to your website, you have a bot linked to your website, small frauds like that happening, how can you detect that this is happening? So, you have your server, there's a page loading. How do we detect this about? The data that we get in the web server is usually something like the timestamp, the time at when the request arrives, the page URL, the page preferred, the user agent, something like this. Where we start to have some useful information, for example, what's the OS, what's the browser, what are their respective versions. We also have received the IP of the connection. From there, we can start to map it out to what's the ISP or the ASN. And from the ranges that are publicly routed on the internet, we can figure out if it's from the data center or things like. And based on all of these signals, we can start to formulate some ideas. In the user agent, if you're using a Chrome headless, it will be written there unless you override it. We can just say, if we find the headless token in the user agent, then this is a bot. If you use an IP that comes from a well-known data center range, we can estimate that it might be automated traffic. If the time patterns are very well or very frequent, very well aligned, etc., we can also estimate that it could be some type of automated traffic. And once we're done with that, we want to take an action. We want to block the page from loading. We want to do a redirect. We just want to monitor the traffic. And if there's no problem at all, we just allow the traffic to pass through. On the other end, of course, we want to report that information to our customers. Let them know what's going on. So we have the real-time handling, and then we have the reporting. So from now on, I'm going to explain how do we do that within our own stack in Elixir. Almost all of our stack is on Elixir, except for some small projects. And when you see the red award there, written in red, that's a specific name within the Elixir ecosystem. So we have an umbrella project, maybe to answer the question about the monolith versus the how they call it? Microservices. I don't care about that at all, because we don't need to care about that. We have a single project. We have 19 apps, which you could call microservices if you deploy them maybe independently. But we just deploy we have three main deploy targets: our dashboard, the job server, and what we will talk about, the tracker. Thank you for your last. And then we have a lot of other dependencies on Postgres, ClickHouse, Redis, BigQuery, Kubernetes, Prometheus, Grafana, Creolog, like lots of things for monitoring, lots of things for operations as well. Elixir doesn't solve all the problems. Erlang also doesn't solve all the problems, but it helps a lot. And we have a global footprint. We deploy to US, Europe, Southeast Asia, and a lot in Japan, obviously. Many of our customers are here. Across, not all of it across all the cloud, but we use services from GCP, from AWS, from Akamai, Pinot. And to scope a little bit the talk today, we're going to just take a look at one of the apps, one of the deploy targets, what we call the tracker. It logs the data and classifies, like I was explaining. Okay. So we're going to look at this problem here from the perspective of an Elixir application. We're receiving a web request, taking a look at the data, classifying it, giving back an answer. And so the process, the sequencing of the process, if you take a look, if I did from a timeline perspective, our load balancer gets a request, passes to our web server, running on top of the Erlang virtual machine. We have something called Cowboy there, which is the web server written in Erlang that reads from the socket all the information, transforms it into an Elixir struct through plug. And from there on, we have access to all the basic features like routing, etc. We use absolutely no framework for this application for many different reasons. So from the moment we've got the request in memory, our pod executes. We start extracting information like the user agent, the IP, etc. The first step. We start doing some lookups. What's the ISP for this IP? What's the information that this user agent gives us? We perform a classification, is it about or not? And then we return that answer as soon as possible through the HTTP response. So the point here is that we must process and respond to that request very quickly. We're talking about the usual time to respond here is within a millisecond. And so we also defer everything else to everything that is not blocking on the critical path sensor is left to be done later. It's left to be done later, but we still want to report in the dashboard. Yeah. So how do we do that? We need to put it somewhere in the database that the dashboard can access and start, break down this data. We have quite a lot of data, so it's not a straightforward process. We start to ingest it, we start to summarize it, create lots of material as use, accumulate the data, embed it from buffers, and then the dashboard family can access through some kind of table that's fast to query. But the transition point here is done through something like a macro batch in Avro. Avro is kind of a CSV file with binary, and you can zip blocks of lines. For example, they call it the data block that you can compress. But hopefully this gives you an idea of what it looks like. What it means is that we need to accumulate a few lines before we write it to the file. We can just write them one by one. And so the way we do that in this application is that once we're done processing the request, we have all the data being memory. We set it to another process for logic. We call it the post processor, then the post machine name here. And all of this is already out of the box. Like we're seeing in the first presentation, the communication, the processes, the communications, inter-processes are features that are built in the virtual machine. We can just call, in this case, churn server cast. We're using a churn server for the post processor, and the data is sent to the process mailbox. The mailbox is just a queue, first in, first out, and then what we get is the capacity to process those messages independently and without blocking the request processor. And here, in this case, our processing is very simple. We just accumulate it in a buffer, and once we're ready, every few seconds, we close it. We compress the rows again to never that block, and we ingest the data. Okay, let's shift a little bit the problem. This takes care about one request, processing one request, but we have multiple product lines and we have many customers as well. All of this processing must be adjusted depending on the type of products, because we'll be looking at different types of fraud, for example, spam versus like a fraud or things like that. So we'll use different classifications. There's some basic ones, there's some that are more tailored for each type of fraud. And also, each customer may want to take a different type of action. They may want to block bots, others want to block everything. And so we must be able to adjust all of this during this processing. But this means that several of these points are dependent on configuration. And you might be wondering, like, why don't we query the configuration in the database? It is too slow for what you want to do there. So what we want to actually be doing here is bring all the information that we need in memory, like we were saying in the first presentations, and just go through this whole process in the left once without having to wait anymore. To do that, we're depending on external APIs. It's still our APIs, and making up this as a microservice here. It's still our APIs, but it's a different deploy target. It's managed different. We have an API that tells us, if there's update from the customer configurations, our thread feed, our GeoAP lookups, so an IP by ISP to the country, spoofing models, different type of models for detecting fraud. All of these are controlled independently of one another. It can be updated several times a day, depending on the type of resource we're talking about. For the configurations from the customers, as soon as they adjust the dashboard in it, or they edit immediately on all the nodes that are processing these requests. So all of these are very independent from one another. In terms of what it looks like in memory, we're talking about an ATS table for the client configuration. There's a struct, a data struct, with all the configurations that we need. And for everything else, it's a binary. Not necessarily a string binary, but it can be like a Rust restores. We'll use some ifs in there. It will be some binary data.
Sure.
We will reference the ones we need for the specific type of processing we want for each customer, and that will be all of it. This raises a couple of questions that we need to handle. For example, now that we have a dependency on that API, what happens when we are rebooting the server and the API is down? If it goes down for any reason, how do we bootstrap our tracker gear? Sorry about that. I've not been able to connect to the Wi-Fi yet. So, how do we boot the node when there's no API available? How do we handle concurrent updates that we're talking about? Because there are some dependencies across all these resources.
Wait, keep us.
Let's open those. And how do we share common resources across processes? We saw in the first presentation that Elixir as mutability, etc., etc. There's a lot, maybe some of you have heard that all of it is basically copy of objects. We don't want to copy these resources. They're actually quite large. That will just kill all our memory. How do we handle all of these smaller problems here in Elixir? So for the first one, we don't use ETS. We use something called DETS. May not be the best thing to use nowadays. I remember we started 9 years ago. And what we end up doing is just serializing all these resources continuously to the disk. Whenever we boot, if there's an API available, just reload everything that was in memory. And again, this is available out of the box, and it's just 1-2 lines of code, okay? For the concurrent updates, we're seeing, again, in the previous presentation, mix of trend servers and some notifications takes care of all the problems. They update all of them independently. You don't care whenever there's an update. We notify everybody, trigger the wall references across each data struct, and keep going. And how we share data? Actually, there's some concept that can be shared across processes. ETS can be shared, larger binaries can be shared, and there's some concept of pointers, not exactly a pointer, but like something called a reference, which is something you can use to just point to some resource that you want. And so copying that is very cheap. The resource itself is not copied anymore. And so in the end, what we have here is all of the data and reference that we need in ETS. And every time we have a request that comes, we figure out which customer data does it belong to. We do one ETS lookup to get all the data that we need, and can do all of the processing all at once. And so with that, we're able to handle quite a lot of requests in parallel, more currently, while merging all of it into a single file at the end and push it for ingestion. Okay, so that's more or less the of the talk right here. Some of the points again. All of this is available out of the box. There's no need for extra libraries. Bringing stuff in memory is very easy to do with ETS. Communication across processes, super easy to do with one-liners. The concept of programming concurrently is almost transparent. It feels like we're programming sequentially, because in fact we are often just programming the code of a single process, which executes sequential, and then we send messages. The concurrency happens just over. With Umbrella project, to answer the question, we have a mix of, in development, we have access to all the monolith, we have access to all the projects, to all the apps. When we deploy, we're careful to remove the things we don't need, and just the minimum amount of apps that are really bad. Elixir is not perfect. Okay, there's a lot of things that are out of the box. We still need to care about, the balance between, in our case, between request processing and post processing. If we don't adjust the volume of things getting processed, it can get out of. So we can have that doesn't matter. Just be careful about Zeeks and all of it. That was in the first talk. I'm going to leave it here if you want to look it up later. There's one very good library for most of the problems we have, or it's already available out of the box. This is what we use, I think. Yeah, that's what we use. One recommendation that I got from a talk in 2015, I think, was to read this book. If you use Elixir in production, or if you're thinking to use Elixir in production, the book is a bit old. So I think it's not been updated since 2016. But it details in very good detail how to debug and what can go wrong with an airline virtual machine running in production. How do you debug that? How do you read the logs? How do you read the crash down? How can you do some introspection across the process and things like that? And it's been very useful. About the low back, just one layer, just on small layer. It really allows for a small team to do a lot on a simple stack, which for us was very good. Yeah, that's it. Thank you.